Okay. Greetings, denizens of the internet. Does anyone have any like questions before we start? Like, where is this class going? What is the point of this class? I am really not having a great time. No? That wasn't a question. The last one wasn't a question, but maybe you have comments as well. No? Having too great of a time. Okay. I try my best. Everyone's on mute, so I'm just talking to myself, but not like it would have been different in this apartment by myself for like a few weeks now. Okay, it is 11:10, so we're just going to get started. Hopefully the resolution of the screen is sufficient. So on the agenda for today are analyzing the salient features of multi-stage amplifiers and kind of introducing the concept of output and input swing, if that hasn't been introduced to you already. We're going to do a small one-stage example of that, and then we're going to look at hopefully 2 examples of simple multi-stage amplifiers where the salient features that I just mentioned kind of come together. So yeah, with that being said, let's just jump right into it. So the first salient feature of multi-stage amplifiers is the gain. So in a lot of amplifiers, we've seen single-stage amplifiers. Oh, we've seen single-stage amplifiers that have a gain, and then they will have some frequency response, but we haven't spent too much time analyzing that yet. And it's in the multi-stage amplifiers where the frequency response kind of gets a little bit complicated. So that's when we really decided to introduce it. But this first attribute, which is the gain, which we've seen from the beginning, can either occur, like the highest gain can either occur at low frequency or DC, or it can occur at like a mid-band point. And the reason why this happens is because in some circuits, like the circuit that I've drawn here, which is a, can anyone tell me what type of circuit this is? Like, what would we call it?
Common emitter amplifier?
Yeah, that's great. It's a common emitter amplifier. And we have added something else that has a name as well. So what is this resistor called in this configuration?
Degeneration resistor?
Right, exactly. So yeah, this is a common emitter amplifier that is degenerated with a resistor. And so the reason why we say degeneration is that this resistor actually significantly reduces the GM of this amplifier stage at kind of the reason why we do it is because in this case BJTs are actually incredibly difficult to bias directly from a base to emitter voltage. So we need to add this resistor here in order to make the bias of the circuit stable. And so when we do that, that's kind of because the BJT is designed this way, we can't really get the desired amount of gain out of the circuit without adding some additional stuff in order to increase the gain from the degenerated gain. So I think we might have analyzed this in a lecture or something. So I'd encourage you to look at that or the notes for the specifics of this topology. But the important thing to note here is that if we put a really, really big capacitor at the emitter, then certainly, at DC, all capacitors are open. So the gain is going to be kind of bad just because the degenerated common emitter has pretty bad gain with respect to a normal common emitter. But we can ensure that this stage will have higher gain as we move from the DC low frequency 0 to a slightly higher frequency if we can make this capacitor short out So capacitors will progressively short depending on how large of a capacitance they are. And so if we put a very large capacitor here, then this capacitor will short at an earlier frequency, and then we'll see what is actually in the small signal world just a normal common emitter amplifier, and then we'll see a much higher gain than we would have seen in the degenerated case. So that's how we get to the mid-band, and that's why the gain there is higher. And then another thing that we're going to analyze is when the mid-band ends. So when the frequency response begins dipping again after we get our highest gain. So yeah, the first thing is gain. Gain we've seen already. With that being said, we can move on to the new thing that we're going to introduce today, which is output swing. But before we do that, do we have any questions about this example or about mid-band gain versus low frequency gain versus another type of gain? No questions? Okay. All right. So with that said, we'll move on to the output swing. So output swing is this concept where we want to know how much the large signal voltage at the output can swing such that the amplifier remains operational or on in a sense. And one criterion for an amplifier being on that we've established in the past is that we kind of want all of our transistors to be in saturation, because that'll ensure that for the current sources that they have sufficiently high output resistance and that they are not changing their current too much according to what's happening in the circuit. And then for our amplifier transistors, that they have sufficiently high GM and RO for amplification to happen. So, that's a condition. We want the transistors to remain in saturation. So how can we constrain the...
Shit.
Welcome.
It's already like halfway done.
How can we constrain the large signal output voltage such that both of the devices here remain in saturation? So that's something I want you to think about. So think about it for the next 1 minute, and then I'll give you a little hint, and then I'll give you another minute, and then we're going to get an answer after that. So go ahead, think about it. Or maybe I should put you in breakout rooms. Did I ever forget how to do that?
Nah, that's all right. I feel it always takes a while.
Let's do. All right.
I mean,
goodbye.
we also have like 6 people, so I think
Yeah,
we could also just make this one.
No, you're invited to breakout rooms.
Okay, I see it.
No.
I see it. I'm joining.
Let's go to the breakout room. What happened? You guys just left?
I mean, we talked about it.
Okay. All right. I'll close the other.
We completely solved it.
All right. Okay. It's a solved problem. Stay safe. Well, Josh, Mark, and Nilesh are in deep conversation. Also, you lost Liz. What did you do to Liz?
She also left. I don't know.
I think she left the meeting. Oh no.
Oh,
Guess we all have to figure this out.
yeah. Also, I would not doubt if Nilesh and Mark were not talking about this problem.
Well, we'll find out. We'll see. All right. Okay, so we've only lost Liz along the way. Bye, Liz. Hopefully she finds her way back. Right. So, okay, I guess you know, does anyone want to tell me what their intuition is? Or actually, Rahul and Rami said they completely solved this problem. So, how about we?
Oh yeah, we did too.
You did too. Okay, we can hear from you later then. Well, let's.
All right,
hear
Rami,
from you.
let's see what you guys got.
Rahul, you want to talk or I talk?
All right, I can talk. Well, so
Sure.
if V out swings too low, you'll push the NMOS out of saturation. So you need V out to be at least a VD sat, which is like VGS minus VT. And then similarly, if it goes too high, you'll take the PMOS out of saturation. So you need it to be like VDD minus VD sat is the upper limit. And again, VD sat is, I guess, VSG minus VTP, absolute value of VTP.
Right, exactly. That's exactly the answer. Okay, so VDSAT is one name for it. I think VDSAT is probably
Overdrive voltage.
Yeah, VDSAT is probably the best name for it because this definition of overdrive voltage does not always correspond to VDSAT. So the thing is, you know, in the model that we have shown you, VDSAT is going to be VGS minus VT, or you know, whatever absolute value of VGS minus VT. If it's like a PMOS. But the thing is, in other device models, sometimes this doesn't. It does, like, so this will always be the definition of overdrive voltage, but the overdrive voltage is not always the same as VDSAT. So in this case, yeah, equals VDSAT in this case.
Why?
Yeah.
Why is it not always the same?
So in really short channel devices, lots of weird things happen. So that's not the focus of this class. So I don't want you.
Okay. Yeah.
So, so right, you know, to kind of dissect what Rahul said, we're going to need the saturation condition for both of these transistors to be satisfied. So on one side, we have VDS being greater than VDT, and then we also need that VDS is greater than VGS minus VT. And, you know, whatever needed absolute value signs are going to be thrown in there for a PMOS. So let's see, in this case, we have a top and a bottom transistor. So, oh, oops, I do this better. So, bias, okay, Vn, yeah. So, you know, if we're going to be looking at each of these transistors, the condition here is that V out should be greater than VDSAT of the NMOS. And then the condition here is that V out is less than VDD minus VDSAT of the PMOS, right? You know, absolute values wherever necessary. And so the net peak-to-peak output swing is VDD minus VDSAT PMOS minus minus VDSAT NMOS. And if we say that these are nominally equal, these two VDSAT values, nominally equal, then we see that the net peak-to-peak output voltage swing is VDD minus 2 VDSAT, which is a pretty useful metric because the intuition that I'm kind of trying to convey here is that we see that the full swing from rail to rail is VDD. And essentially for each transistor, we count that there is a VDSAT here and a VDSAT here. So we have to kind of paint the picture that analog designers like to paint. We are kind of reducing the headroom of our signal. So for every transistor, we lose a VDSAT. And so what we end up with is, in this case, because we have two transistors, we end up with VDD minus 2 VDSAT as the peak-to-peak output swing. And then I guess based on that, this gives us a constraint on the input swing. So, okay, so does anyone know what the gain of this circuit is? So
It's
this
probably gonna
time,
have something to do with GM.
yeah, it definitely has a GM in it. That's a good answer.
Yeah,
That'll
dude.
get
Intuition
you-
right there. Electrical engineer intuition.
That'll get you at least 2 out of 10 points on the final.
Excellent.
Well-
Excellent. Excellent.
It has an RO looking down and an RO looking up. So it'll
Yeah,
just
that's
be
really
like-
great.
Right. Yeah, that's another really good point.
Yeah, so we're looking at the output node, looking down because this gate is disconnected from this node, and it's not, and it'll be like if we're doing a Thevenin equivalent analysis, it's going to be grounded. So looking down, we're going to see an RO, and then looking up, we're going to see another RO. So that's basically that's half of the battle. And then Mark said GM is the other half of the battle. So the answer is going to be the small signal gain is going to be negative GM of the NMOS times RO of the NMOS in parallel with RO of the PMOS. Okay, so with that gain, we can actually form a constraint on the input swing, now that we've constrained the output swing this way. So how much can the input large signal voltage vary before we get some railing or some kind of or undesired characteristics at the output, essentially? So you can assume that this small signal linearization of the gain basically holds as long as the device is working, although that's kind of a very rough assumption. But making that assumption allows you to, kind of point out some useful things about this circuit.
Can we also assume that like the swing is symmetric on either side of the output bias?
Well,
Yeah,
it
that's
would depend
really
on the
important.
bias.
Wait, I
though,
couldn't
right?
hear
'Cause
anything.
it could be like floating.
Yeah, so we're gonna first assume, so that's a really great point. So first assume where would we like V out to be biased to allow for, if VDSAT is the same for both of these transistors, where should V out be such that we have maximum output swing?
Halfway between
Exactly,
VDD
yeah.
and ground.
So assume V out is equal to VDD over 2 at DC. So yeah, in the case that the VDSATs of these are not the same, then you're going to have to constrain it based on that. So if like this VDSAT is larger, then we kind of want this to be a little bit lower, such that we account for that the fact that we have less headroom on the top. So making that assumption, so if we make this assumption, then we have the fullest possible output peak-to-peak voltage swing. And then using that, we can find the input swing, assuming that the input is also biased at kind of an optimal point. So the second assumption is that assume input is also optimally biased. So does anyone have at least a strategy for getting us started on that?
Getting started on showing that it's optimally biased, or do you mean on solving what the input swing would look like?
The second one.
Well, it would just be the output swing scaled down by the gain. So it'd be, just basically take whatever constraints you had and divide by negative GMN R on divided by R op.
Right, exactly. So if you if you think about it, essentially, we're going to have some varying voltage over here. And what's going to happen is that it's going to be increased. It's going to be scaled by the gain to the output, such that we have a just larger varying voltage at the output. And so if we have some constraint on the max output swing, then if we just divide that constraint by the gain, then we're going to get the same constraint for our input. So the peak to peak, max peak to peak input swing is therefore going to be output swing divided by the gain, or the absolute value of the gain. And that's going to be, in this case, VDD minus 2 VD set divided by the gain, which is GMN, times this output resistance term. So yeah, this is just kind of a very useful concept when you're designing amplifiers. I'm not sure it's going to show up too much in this class, but certainly if you take 140, you're going to see this kind of idea all over the place. So I just wanted to touch on that. Okay, with that being said, we can move on to the kind of last attribute of our agenda. Let me look at it again. So yeah, so multi-stage amplifiers have a gain, an output / input swing, and they also have frequency response. Frequency response. And we spent okay, just mute yourself, Mark.
Oh, yeah.
We spent last discussion analyzing methods for kind of distilling a frequency response from a relatively complicated looking circuit, and that method is called the OCTC method. So to summarize, we can identify poles based on node capacitances and equivalent resistances. And the second point is that we can approximate the bandwidth of the circuit as the sum of those pole time constants. So the tau values are going to be, tau I is going to be Ri times Ci for each such time constant in the circuit. And then the net bandwidth, according to the derivation that Ollie showed in lecture, is going to be about 1 over the sum of those time constants, which in the case of a dominant pole, the bandwidth will approximately just be 1 over the dominant time constant. So, you know, this is the kind of approximation that we use a lot when we're actually designing amplifiers, just because it makes our lives easier. But the more accurate assumption is actually this one, and this is the one we want you to do on the homework. So just keep that in mind. Also, can anyone tell me what the units of this one is going to be?
Radians per second.
Right, exactly. So so this tau is a number that's going to be in seconds, but it's actually 1 over tau is actually an angular frequency. So just remember that the units of this are radians per second. And I've gone through periods in my life where I have understood why that's the case, but now is not one of them. So I can't exactly tell you if you ask me, but it's something that you can look up and eventually piece out yourself. But this is definitely a fact though, so keep that in mind. Okay, do we have any questions about OCTC or like this kind of expression or anything like that?
So for the bottom approximation, do we assume that there's so the dominant pole on the high side makes sense because that's what's setting the high frequency cutoff, but If we're saying that the bandwidth is equal to that, then that assumes also that there is no low frequency constraining pole, right?
Right, yeah, this is very much an approximation. So if we have the mid-band case, like with the degeneration capacitance and resistor, the bandwidth is not, this expression for the bandwidth is not really going to account for that. I mean, you could include the degeneration capacitance in your time constant analysis here, but it doesn't really fall into, so the core assumption behind this analysis is that your transfer function is of the form some constant times 1 plus s omega 1, 1 plus s omega 2, and then n many poles. And so if you think about it, this transfer function doesn't actually fit the case where we have like a mid-band gain. So in that case, we have basically like very low gain at DC, and then we rise in gain at some point due to the capacitor, and then we flatten out, and then we drop again. And so that requires a few zeros, or actually at least 1 0. So this approximation doesn't include any zeros at the top here, so it doesn't really fit that case. So that's a good point to make.
Okay, sounds good. Thank you.
All right. Any other questions about that? No.
Sorry, you probably said this earlier, but did you record this session?
Yes. Yes.
Okay, awesome. Thank you.
Are we all good otherwise? Okay. So with that being said, we can do some multi-stage examples. So let's do one. So no, I screwed it up already. Okay, so this is going to be a cascaded common source amplifier. So what would happen if we did something like this? V bias 1, V bias 2, Vn, and this is V out. So hopefully everyone is writing this or drawing this circuit down, and because breakout rooms are in your future. So the things I'm going to want you to find are the gain, output / input swing, making all the optimal assumptions, because I don't actually want you to work that hard. And then also frequency response using OCTC. And you need to tell me which poles could be dominant. And the last assumption that you'll need to make for that is that you have some, over here, you have some load capacitance. Like that. Okay, so I'm going to give you 15 seconds to draw that. Actually, no. So you can start drawing it if you're done drawing it, or if you've memorized it, just throw up a yes in the participants thing, and then I'll send you to your breakout room gulag.
Okay. Okay.
Okay. All right. And yeah, if anyone hasn't done it yet, then I'll you can ask your friends in the breakout room. So
This is a homework problem.
this is a homework problem?
Oh wait, no, it's not. You changed the transistors. Never mind.
It's a homework
Yeah.
problem? I wrote
If the top
wrote-
loss had been an NMOS, it would be a homework problem.
Oh, that homework problem. Okay. Okay. Maybe.
Wait, which homework problem are we talking? Okay.
Maybe the first one. I don't know. It's okay. Whatever. It's not a big deal.
Don't worry, but you'll see it when you get to it.
Okay, that's not nice. Anyway, go to your breakout rooms.
Wait, what? That was fine.
Out of here. Get out of here. right. Well, you must have been in very deep conversation because no one came back early this time. Okay, so yeah, so I mean, I kind of have the answer for the gain here, kind of sitting there. So does anyone want to walk me through that one?
Oh, so it was going to be GMR over 4. Okay, so we don't have to take into account the capacitor. Interesting. Yeah, so what you could say is that the GM, so we look at the first stage and we say like, okay, we can see that we're going to have a, you know, on our input, we're going to see that, you know, so our gain is going to be, our transconductance times our output resistance. And so our output resistance, because we're going to have no current going into the M3 transistor, we can just treat this as like a V out. And so we can say, like, okay, our output resistance is going to be RO over 2 because the RO of both M1 and M2 are the same. And you multiply that by the transconductance, which in this case is GM. And then from there, what you can do is now you can take a look independently at the right stage. And the right stage is gonna, we're gonna have again, our RO over 2 for our output resistance multiplied by GM, which is our transconductance. You multiply your two stages together and you get your total gain, which in this case is going to be GMR over 2 squared, which is what exactly you have.
Yeah. So yeah, that's more or less it. So
now our question was why we thought that you might need to take into the impedance of the load capacitor into account for your output.
Right. So I included the capacitor. So when I say gain, I mean gain at the highest point. So like gain when the circuit is nicest looking, and usually that means that it's at a low frequency where the capacitor has not begun to short yet. So if you think about it, the impedance of a capacitor only becomes relevant when it's beginning to get low. So you know, a capacitor impedance is something like a pole at the origin. So if the curve, I mean, at least to me, it looks like this. So it starts off super high, and then it goes down to 0 at some point. But what I'm kind of asking, like generally when we ask these problems, we're asking you to assume that the capacitors are opens mostly, unless they're super large, in which case they're shorts. And so this load capacitance isn't that large, so it's not a short. If it was a short, then effectively you basically wouldn't have anything happening at the output from, or the second stage, that is. So the GM would just be shorted out, and the RO would also be shorted out, so the output would just be 0. But yeah, so we account for the effect of the load capacitance when we do our frequency response OCTC analysis, because when we analyze the gain, then once we can find the approximate bandwidth of the circuit, then in our minds we can construct an image where we have a transfer function that looks like this gain that we found here at low frequencies, and then at the bandwidth, so at the bandwidth that we calculate, it begins to fall off. But before that point, we have the gain that we calculated. Does that make sense? So either it makes a lot of sense.
Okay. Yes, no, so it makes sense. Yeah, so we're assuming we're going to be at low frequency. Yes. in that case, okay, so no, so that answers one question I had. And the other question is, isn't it for the first one, because we're going into the NMOS, wouldn't it be negative for the first stage?
The gain.
Yeah.
Yeah. I mean, I think it does. Both of the gains are negative. That's why I put two negative signs. And
Those are
then
both negative, but aren't you going to a PMOS for the other one? So wouldn't it be not negative?
PMOS is actually also a negative gain.
Oh, okay, so it's negative times negative. There should
That's
be.
a good one to do under that time.
It's positive when it's common gate.
Yeah, there are. So actually, I think that. So depending on how you define the common gate topology, like where the input is going, then it can be positive or negative. So I never really remember that one. But the common drain is always a positive gain, and the common source is always a negative gain. So, yeah. Anyway, so we found the gain. Good job, guys. Now we move on to output swing. So I said, what I have written here is that it's the same constraint as before. Can someone explain why it's the same?
So before we said it was VD minus 2 VD sat. Well, yeah, so our two stages are pretty much independent from one another because we know current going into a gate of M3. And so we can look at, if we want to look at the output swing, like limit, then you can just say like, okay, if we obviously see that it's going to be VDD like minus the overdrive voltage of these two transistors, and adding having two stages here doesn't really change that because we can treat them independently. And so yes, that's pretty much it.
Yeah, so the condition on this large signal voltage here is not changed. It doesn't really depend on this stage at all, actually, and it didn't depend on that and on the input at all in the first place. So we still have the case that our output swing is going to be VDD minus 2 VD set. But in this case, we do have a different input swing. So can someone walk me through the input swing? Maybe I didn't ask you to do, or I did ask you to do that. So.
Yeah, so with the input swing, what's happening is that now.
Let's try someone other than Mark.
Yeah.
Just to make sure everyone else is following along. All right, I know the rest of you are here. I've heard your voice.
Nilesh, you want to take a shot?
I mean, sure, okay. Actually, yeah, so we just got that it was going to be the output swing divided by the gain again. But you're indicating that that's wrong. So.
No, that's right. It's right. It's the
same.
same.
That's right. And here's the gain is different, so that's why it's different from before.
Oh, that's what you meant. Okay, not conceptually different, just numerically different. Okay.
Yeah.
All right.
So could you say it out for me?
Sure. It's 4 times quantity of VDD minus 2 VDS sat divided by GMRO whole squared.
Yeah. So GMRO squared divided by 4.
Yeah, and then we just brought the 4 to the numerator.
Yeah. So in this case, we actually have, do we have more or less input swing this time?
Less.
And why is that?
Because the gain is larger. And so
and the gain is actually, so this GMRO squared over 4 value is actually pretty high as far as this goes. So, without using other cool circuit tricks, this is about as good as you can get from single stage amplifiers, especially when they're used in this way. So yeah, GMRO.
Wait, so is this a single stage amplifier or is this a 2-stage?
This is a 2-stage amplifier that is made using single stage amplifiers.
Right, okay, all right.
Although there are more refined ways to make multi-stage amplifiers, which hopefully we'll have time to get into, maybe not. But yeah, so GMRO is typically around 100, at least for getting on long channel devices. So those are the devices that we talked about in this class. So 100 squared over 4 is a decently large number. So it's pretty good. And now we can do the frequency response. So I don't know, this kind of always gives me the heebie-jeebies, but like you can draw these capacitors in, and I guess they're typically drawn like this just because it's either expedient, but it kind of looks like they're parasites on the circuit because they're small little things that are like holding on to the nodes, kind of gross. So I've drawn in all of the parasitic capacitances here. So can anyone identify, and what remains is that we also have this C load over here. So that's also
What's the Miller effect?
What is the Miller effect? Can anyone tell me that? It's a good question.
I know it has to do with capacitors.
It does. Well,
It's
it does. Yeah. So we did this last discussion, right? So does that? Does
But yeah,
anyone have an answer?
it was a little over time, so I unfortunately had to go. But
Yeah, I mean, it's basically when you have a feedback capacitor, which is any capacitor connecting the input of a transistor to its output. You can divide that into two equivalent capacitors, one at the input, one at the output. The one at the output is typically, assuming unilateral transistors, it's just going to be, on the output, it's going to be the same feedback transistor going to ground directly. And on the input, it's going to be a 1 minus A times gained version of the feedback capacitor also going to ground.
So this is the net takeaway from what Neil said, which was, I think, completely correct. So if we have a capacitor that is flying across an amplification stage, so to write it out explicitly, if we have a V in here, then this V out is going to be A times V in. If we have this sort of situation, then we can simplify the circuit into this circuit where instead of having a flying capacitor, we now have a capacitor that goes to ground at the input, and then we also have a capacitor at the output that goes to ground. So when A is a large negative number, what's going to happen is that this 1 minus A term is going to be very, very large. And so this input capacitor is going to be super large, whereas this term is going to be relatively small. So we're not going to care as much about it, but it's still relevant. So yeah, using that kind of analysis, we can identify the dominant poles. So does someone want to point them out for me? Kind of which nodes do we expect to have a lot of capacitance and a lot of resistance? So dominant pole nodes. A lot of C and a lot of R. Any ideas? So I'm going to provide a really bad idea. How about ground? Okay, ground is not where the dominant pole is. Okay, so the ground shows up in a few locations here. So it's at the gate here, it's at the source here, the gate, the source, and all the body terminals as well are all small signal ground. So that actually, it sounds kind of stupid when I said it like that, but I think that actually does provide a rough constraint on which poles can actually contribute, because it's definitely not this one, 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 or this one, or this one. So we only have so many nodes left that could contribute. So yeah, any thoughts?
So the Miller multiplication is going to make the outputs of each stage have large capacitance, or the inputs. Yeah. Sorry. So
yeah.
Maybe so the top right, the Miller cap at the gate, maybe, and then also depending if C load, the output of that. So maybe those two.
Right. That's exactly correct. Thank you. So this node, so the input to second stage is one of them, and then the other one is the output. And so what we have in this situation is that because the R in from the source over here, this is the total input node, because the R in there is 0 in this case, we don't have any pole here. But in like other situations, you could have some non-negligible R in here, so that would also be a pole you need to consider, because this capacitor over here is a Miller capacitor. So in this case, that's not an issue, but in other cases, that might be an issue. In this case, though, we do have, definitely we're going to have this capacitor over here, which will be very large, and then we will have some non-negligible resistance looking from this node. And then at this output node as well, we have a relatively large C load. I didn't tell you the value, but you can usually assume that it's relatively large. And then we have some other parasitics as well, and then we also have a relatively large resistance. So Maybe as the last thing we do.
I was there
today.
no RN. Like I thought, doesn't the gate have infinite impedance?
So the RN wouldn't come from the gate, but it would come from the source, the input source.
Oh, right. Okay, fair enough. And then I thought that we were saying that it wouldn't be any capacitors that go to ground. So why would C load be one of them?
C load goes. So what I said was that there won't be any poles associated with nodes that are ground.
Oh,
So if a node is ground, then that means that any capacitance that is
Right.
it and ground is shorted to ground. So that's kind of what I
Right.
meant.
Okay. Yeah. So for example, the one between the gate and the source for M4, for example. Yeah. Right. Of course.
Yeah, exactly.
Okay.
So if we find the time constants for these guys, so this time constant, this is the input here to the second stage. So what is the effective resistance that we see from this node? We've actually already found it before.
Looking back, isn't it R over 2?
Yeah, exactly. So the effective resistance is R over 2. The presence of the gate doesn't load the circuit, so it's not a problem. We have R over 2, and then we have a few parasitic capacitances. So we have like, what did I call them? This is like M1, M2, M3, M4. I'm going to go slightly over time just to finish this example, but it's going to be the last thing I do. So for this discussion. So, right. So we have some capacitances. So there's this one over here, the CGS of M3, CGS3. And then we have, we're going to account for this one later. We have this one over here, which is the CGB of 1. And then we have these. Actually, we have a few more. We have this one, and this one. So we have a bunch of parasitics. I'm just going to write sum of parasitic capacitances. C parasitics. And then we also have, this is also a parasitic capacitance, but it's particularly noteworthy just because it's a Miller multiplied capacitance. So what we end up over here is we have CGD of 3 times 1 plus the absolute value of the gain here. So the gain here is going to be what we found before, GMRO over 2. And so this will usually actually, because if GMRO is like on the order of 100, then this will definitely dominate these, the sum of these. Although these only make your pole worse actually. So it's not necessarily a bad idea to include these. So depending on how much gain we have, this could actually be a pretty significant pole. So that's one of them. And then the other one is for the output. So this one, we can sum up the parasitic. Well, so what is the resistance looking from this output node as well?
R over 2 again.
Yeah. So it's the exact same situation. In this case, the first stage does not affect our analysis. So we have R over 2, and then we have some other parasitics, and then we have our C load. So this is actually like very ripe for a comparison because we have the same equivalent resistance at each of these nodes. And so all we need to do to compare the poles between them is to see how much parasitic capacitance there is. And if, in this case, if C load is less than, these parasitics will be on the same order, although they won't be the same exactly. If C load is less than CGD of 3 times approximately this gain from here to here, then actually this pole can begin to dominate, which is not something you would assume in general, because typically, if you look at a schematic or a layout, you're going to have a CL that's very large, and then, generally you want to assume that the largest capacitor that you've already put in there will dominate. And this is kind of proving that because of the way you design your circuit, that might not necessarily be the case. So that's just something to look out for. And I think problem 2 more or less is kind of intended to solidify thinking like that. So, if you don't have any more questions, I think that's about it for today. I still have my office hours at 3:30, so come on by if you have more questions.
Sweet. Thank you so much for your help.
Thank you.
Yeah. Thanks everyone for participating today.
Thank you.
Yeah.
Thank you.